Hi everyone. In this video, I want to just finish up a few things from sort of the section on limits, and then we'll sort of move into talking about continuity and some properties of or some properties that follow from continuity. So I just quickly wanted to point out, we spent a lot of time last time talking about limits and sort of formally the definition, but I want to just sort of point out theorems 2.8, 2.9, and 2.10. And in particular, I want to point out that, well, at least 2.9 and 2.10 are things that we've seen before. So when I say the algebra of limits, right, this says something about, like, right, if I know the limit as x approaches a of f, and I know the limit as x approaches a of g, then I know that the limit as x approaches a of f of x plus or minus g of x is equal to the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x, right? And then it does this for multiplication, division, multiplication by a constant, those sorts of things. So I want you to kind of take both of these theorems and for these two, go back and compare them to what we saw in chapter 1. And sort of think about, you know, in what ways are these the same, but in what ways have I had to modify these definitions and these theorems because of the way I've modified the definition of the limit. So in particular, you'll notice phrases like, you know, let A be an accumulation point of the domain of F, like start to pop up. So you'll see that, you know, because we've generalized this idea of a limit to not just sort of being on a nice, not having to have a function that's defined on a nice open interval around a point, because now we just require that it be an accumulation point of the domain. We've also had to change these theorems, but they're really sort of exactly the same theorems in spirit, and really the proofs are sort of fundamentally the same, except again you need to change some things around. So look at those two very carefully. This 2.8, you know, also look at the proof there, mostly because it's an example of a nice type of proof. So this is sort of the first example I think we have of a uniqueness proof. So essentially, I haven't written out the full verbiage here, right? But this says that if the limit as x approaches a of f of x exists, then it's only equal to one value, right? There can't be, you can't have the limit as x approaches a is equal to 1 and the limit as x approaches a of f of x is equal to 4. It can only equal one value. So that's another proof. I think, you know, it's worth reading through and understanding what's going on. So I want to focus today, though, on continuity, right? And this is sort of the natural progression of things, right, from calculus, right? We look at limits and then we look at continuity. So, right, the normal sort of definition we have for continuous, right, is a function is continuous if at a point A, if the limit as x approaches a of f of x is equal to f of a. And as we've discussed before, I mean, this is a little already a little overloaded, particularly in the sense that this is really saying three things. It's saying that the function is defined at the value a. It's saying that the limit as x approaches a of f of x exists. And then finally, it's saying that the limit as x approaches a of f of x, that value is equal to the value of f evaluated at a. So this is sort of our old definition. But we want to look at and sort of see immediately that there's sort of a problem here. And so, for example, consider this function, and I'm thinking this is a function from the set of natural numbers to the real numbers. And so this function is just going to be f of n is equal to 1 over n. Now, when I look at this, right, there's a part of me that sort of, you know, has this deeply ingrained sense from maybe even like high school that, right, continuous functions are functions you can draw without lifting up your pencil, which is kind of garbage analytically. Because, you know, I also, when I look at this, I kind of think, well, I don't know, if I looked at the function f from r to r, such that f of x is equal to 1 over x, then this is, you know, let me maybe sort of draw that in a different color here. I draw this in green, right? So I look at this, I mean, this is a nice continuous function, at least everywhere except 0, right? So, you know, on the one hand, I feel like this is a bunch of dots, so maybe it's not continuous. On the other hand, this is just sort of the restriction of a continuous function to a different set. Like I feel like it shouldn't be that much of a problem. So I've got to somehow deal with this. And sort of the question you can sort of see is that if I try to apply this definition, I'm going to have an issue because this limit is not going to be well posed. So this is a phrase that's often used. Basically, this limit isn't going to make any sense because limits can only be defined when this a value is an accumulation point of the domain. And here, this isn't, I mean, these are all isolated points, right? They're not, they are not, none of these are accumulation points of the domain. And you can run into this in sort of more, more unique ways. So for example, the book sort of points out, if you go back to that example of sorry, I lost my train of thought here. If I go back to sort of this example from earlier, so last time I think maybe we didn't look at this one, but it doesn't matter if we looked at it last time or not. So like, you know, look at the limit. Let me just look at the function. So x squared minus 1 in absolute value is minus 1. So if I were to draw a graph of this function, right, this is only going to be defined when the quantity under here is positive. The quantity under here, you know, I have to ask them when will that be positive. So when will x squared minus 1 be greater than 0? That'll be true when x squared minus 1 is greater than 1. So when will this be true? This will be true when x squared minus 1 is greater than 1, or x squared minus 1 is less than negative 1. And sorry, actually, these should have equalities here, just to be careful. So when will this happen? This will happen when x squared is greater than or equal to 2, or when x squared is less than or equal to 0. This is where I pause for a second because I feel like I've made a mistake. So what mistake have I made here? Okay, let me pause and find my mistake quickly. All right, no, I haven't made a mistake. We're doing great here. All right, so when is x squared greater than or equal to 2? Well, that happens when x is greater than the square root of 2, or x is less than negative the square root of 2. Or I should put equal to on all of those. When is x squared less than or equal to 0? Well, x squared is never less than 0, but it can be equal to 0, and that happens when x is equal to 0. Okay, so this function is only defined at 0, and if you plug in 0 here, you'll get a value of 0. And it's only defined then when x is greater than square root of 2, and the graph looks something like this, or when it's less than negative square root of 2, which looks something like this. So if you look at this function, again, you have this sort of issue, right? I feel very comfortable saying that it's continuous on the interval minus infinity to minus 2, and on the interval square root of 2 to infinity. But what about at 0, right? And again, the issue that we see is that 0 is not an accumulation point of the domain. So then, I mean, much of analysis is about writing down a definition and then seeing, you know, whether it makes sense or not. And so we make a choice here, and the choice is essentially that when we define continuity, we want to either sort of require either require that our usual definition of continuity holds if I'm at an accumulation point, but if I'm at an isolated point, then just sort of don't worry about it and call it continuous. Okay, so that's essentially what our modified definition is going to do. Okay, so let's see what that says. So here's our definition. So let f be a function from some set D into R, and let A be a point in my domain. Then f is continuous at A if either, I'm writing this just slightly differently than the book to emphasize something. So if, okay, sorry, if A is an isolated point, or 2, so if A is not an isolated point, then it's an accumulation point. And if it's an accumulation point, then this limit is well posed. And so we can talk about this limit, okay? So essentially, like I said, what we've done is we've just sort of put, if A is an isolated point, then good enough, we'll just call the function continuous there. If A is not an isolation point, then this limit will be well posed. And if this limit is well posed, then I can take this limit and I can try to compare it to f of A. Okay. So again, we have to modify our definition of continuity. Our definition of continuity from Calc 1 will not make any sense for this function. So we modify it, but again, that modification is a choice. So we'll see what, like, a reasonable question to ask is, why not just say that at an isolated point it's discontinuous? I mean, it's sort of perfectly reasonable. We'll see in some places where it actually works out better, sort of, you want to have sort of nice statements about other things, like things that follow from continuity. And so it actually works out better to sort of let, to define a function to be continuous at isolated points of its domain. But again, it's really a choice. You could say it's discontinuous, and then you would just have to change subsequent theorems based on that. Okay. So let's look at some examples then. So the first is sort of, I want to just really erase this. I mean, let's go back here, right, to this example. I'm looking at this, right, we already agreed that we were good from negative infinity to negative 2, and or to negative square root of 2, and from square root of 2 to infinity. Okay. But then what about at 0? Well, now at 0, 0 is an isolated point of the domain, so my function is continuous there. So here, we would say that this function is continuous on its domain. Right, because it's continuous at every point in its domain. These other points say at 1 is not in the domain of this function, so we just don't even worry about it. Okay. All right, let's look at another example. So let's go back to May's function from before. So if you'll recall, this was a function that we're really just going to consider it on the interval 0, 1 into R. That was defined as T of X is equal to 1 over Q if X equals P over Q is a rational number, and 0 if X is not a rational number. Okay, so let's kind of again go back to last time. What did we observe about this function last time? We observed last time that the limit as x approaches a of T of X is equal to 0 for every a in the interval 0, 1. Okay. So a couple of things here. If I want to think about continuity of this function, the first is to notice that the domain of this function is a closed interval 0, 1. That means every point is an accumulation point of the domain. There are no isolated points of the domain. Okay? So when I'm thinking in terms of continuity, I don't get anything for free in terms of something just being an isolated point of the domain. So that means that my function will be continuous everywhere where my function value is equal to this limit. Okay. Well, where is my function value equal to this? It's equal at exactly the irrational values. So this function t is continuous on the set of irrational values in the interval 0, 1. So this is just well, I don't know, it's a supposedly shorthand way of writing irrational values in the interval 0, 1. Actually, that's actually kind of a dumb way to write it. I should write it like this. Take the interval 0, 1 and delete the rational values. Okay. So t is continuous on all the irrational values in 0, 1. It's discontinuous at every rational value. Okay. You know, this is sort of, I mean, I really hope, this book is very, certainly meant to be read, which you can't really say of all analysis books. The quote from Hermite to Stilichus, I mean, and right, this is not, I mean, this is 130-ish years ago, but in the history of math, that's not a long time ago. I mean, people really sort of, there was a group of people who viewed these examples as sort of contrary to what math should be about, because they're these really awful sorts of functions. And so in particular, Hermite's talking about, you know, functions that don't have, I mean, he's actually talking about like even not so bad set of functions, which are functions that don't have derivatives. I mean, this is an example of that. But like this function, it's not just that it fails to be differentiable. It's not even continuous everywhere. And the set that it's continuous on is this sort of ugly set in some sense. So this is just another example here. The next thing, and again, this is sort of not surprising, and we won't spend a lot of time on it because it's so similar to stuff we've seen before. Get rid of this. Okay. So this is theorem in your book. It's theorem 2.11. And this is essentially just the algebra of continuity, right? Right, so this essentially says if I have a function, two functions f and g who have the same domain, and they're both continuous at a point A, then any constant times one of those functions is also continuous at A. The sum of those two functions and difference of those two functions is continuous at A. The product is continuous at A. And the quotient of those two functions is continuous at A as long as the denominator function is not zero valued at A. I'm not going to do a lot with this here. I'm going to walk you through the proof of one of those in the exercise set because there are some things you have to kind of break things into cases. Like if it's an isolated point, then you have to worry about. So I want you to see that there are some sort of technical things to do, but the actual proofs are not really difficult. I mean, they really just rely back to the fact that we have a theorem about the algebra of limits. That's really sort of the big thing. But the important thing about, or one of the, to me, the highlights of continuity is that continuous functions and limits sort of play well together. Okay, and so that's sort of this, I don't really, well, I know why it's a lemma, but most of the hard work is improving the lemma. So if you look at this lemma 2.12, let's see, what does this say? So if a function f is continuous at A, and phi is a function such that f of phi of t is defined, and the limit as t approaches t naught of phi of t is equal to a, then the limit as t approaches t naught of f of phi of t is equal to f of the limit as t approaches t naught of phi of t. So essentially what is this doing? This is sort of allowing us to push limits inside of continuous functions. And maybe also less, this usually isn't the way you apply it, but I mean, this also says that you can do the reverse, right? If I have this limit inside, I can sort of push it outside. That actually does come in handy from time to time, but the way it's written and the way it's often applied is not in that direction. So I actually want to look at the proof of this, because then the theorem that follows is really just a direct consequence of applying some definitions along with the lemma. So let's look at the proof. Okay, every good analysis proof begins with let epsilon greater than 0 be given. So what do I know? I know my function f is continuous at a. Since f is continuous at a, there exists a delta 1 so that when x is in the domain of f and the distance from x to a is less than delta 1, then f of x minus f of a is less than epsilon. Okay, so this is just a simple statement of sort of what it means. Since f is continuous at this point a, then this is satisfied. All right. So secondly, okay, I now have some control on this, but if I look at this, what I really want to show is that f of phi of t is getting close to f of this thing, which is a, right? I've defined to be this value a. Okay, so I really want to kind of have f of phi of t here, but then I have a different variable I have to do. So now I need to say something about, I need to use this limiting statement. Okay, so let me do that. Let me just sort of write out what this means. So since since the limit as x approaches, as t approaches t naught of phi of t is equal to a, then there exists a delta greater than 0 there exists a delta greater than 0 such that when 0 is less than absolute value of t minus t naught is less than delta, we have phi of t minus a less than delta 1. Okay, so think about what this limit means. Normally we think of a limit as saying, you give me any epsilon you want, I can choose a delta so that these two things will be that close together. Well, it's almost like in the second statement, what we're using for our epsilon is actually the delta 1 from before. Okay. So we're saying you can choose a delta such that as long as t is close enough to t naught, phi of t will be within delta 1 of a. Okay. So now what have I done? I've shown that using this limiting statement, as long as t is close enough to t naught, I can make phi of t as close as I want to a. But now what I can do is I can make sure that phi of t is so close to a. So I've got now, instead of x, it's almost like I'm substituting phi of t here. Phi of t is now close enough to a that f of phi of t will be within epsilon of f of a. Okay. So combining these, so when 0 less than t minus t naught is less than delta, then we have this, but now substituting phi of t for x here, I have this, which implies that f of phi of t minus f of a is less than epsilon, which implies that the limit as t approaches t naught of f of phi of t is equal to f of a, but what was a? A was just the value of the limit, so this is f of the limit as t approaches t naught of phi of t. Now notice that sort of one of the nice things about this theorem is we're assuming that f is continuous. We are not assuming here that phi is continuous. We're only assuming here that phi, the limit as t approaches t naught of phi exists and at some value a. Okay. But as long as we do that, we get this result. Okay. Now, what theorem 2.13 does is say, well, what if phi was also a continuous function? Well, if phi was also a continuous function, then we wouldn't call this limit a, we'd call it phi of t naught, because phi is a continuous function. And essentially, theorem 2.13 just says, well, if that was true, then over here you'd get f of phi of t naught. But that would actually be a statement that says the limit as t approaches t naught of this composition is equal to the composition evaluated at that point. So you just get that the composition of continuous functions is continuous. Okay. So the real proof is in the lemma, and then actually the theorem really is just a corollary of that lemma. Okay. There's sort of a next bit in the book where they talk about some consequences of monotone functions, and essentially it says that monotone functions can't have really bad types of discontinuities. That will maybe become important for us later, and so I actually want to not focus on those right now, and we'll come back to those when, if we at the end when we get to something where we might need them, then we'll focus on them there. And the reason I want to do that is because I want to sort of give the rest of our time to looking at the intermediate value theorem and the extreme value theorem. So these are sort of two of the three value theorems and they're the ones that follow directly from continuity, right? For the mean value theorem, you need to be able to talk about differentiation, so we'll need to say more for that. All right, so let's first look at the intermediate value theorem. The statement of the intermediate value theorem has not changed at all. So here's the theorem. If f is continuous on AB, again, I'm not generalizing this at all, right? This is still working on the closed interval AB, and K is between f of A and f of B. Then there exists C in AB such that f of c is equal to k. Now, actually, if you happen to come to my colloquium talk, I actually sort of gave you one way of proving this, but it's not the way we're going to prove it here. It's not the typical analysis way to prove it. But notice again, like we haven't generalized this. This is actually exactly the same theorem we looked at before. And the reason we haven't generalized it is, well, I mean, because in some sense you can't. If you start having things like isolated points in your domain, I mean, well, okay, so let's go back. Let's just sort of draw an example here, and maybe I'll need to switch markers here. There we go. Okay, so think about this function. Oh, sorry, not do that. Right, this is a continuous function. Okay, and so let's see. Let's say I took this point to be A, and this point to be B. Okay, so maybe let's assign some values here. Maybe this is 10, and this is, I don't know, 2. Okay, so this says that for any, if this were just going to be true generally for continuous functions, then say I wanted to generalize it to say if f is continuous on its domain. I would have a problem here because this would say that I should hit every value between 2 and 10. So like maybe 8 is up here, right? But nowhere on the interval a to b do I actually hit that value, right? So this really does require, and we'll see why in the proof, it really does require us to work on this closed interval a to b. So that's sort of, and the reason we're not generalizing is because the theorem wouldn't be true. All right, so here's the proof. So we're first going to sort of assume that we're in, when we write the theorem, we say k is between f of a and f of b because we don't really know which one is bigger, and we could write it out, but it would be a lot of notation. So let's assume without loss of generality, that f of a is the smaller of the two. Okay. The proof, it would just be some bookkeeping to switch things around if it actually was the other case. So it really doesn't change the proof at all to make this assumption. Okay, and now I'm going to let S is going to be a set. Okay. And S is going to be a subset of my domain. So it's going to be all the things in my domain such that f of x is less than this k value. Okay. So again, maybe have a picture to go along with the proof. You know, I have some function, maybe it looks like this. Here's A, here's B. So here's f of A, here's f of B, and I've chosen some k value in between. Okay, and so this set S are all the x values where my function is below the value k. And actually, I should point out, because this function could be increasing and decreasing, this is a nice connected interval here, but it doesn't need to be a connected set. It could actually be a disjoint union of intervals, of open intervals here. Okay. All right, so I'm going to define this set S. Okay, now what do I want to use this set S for? Well, I want to take this set S. So first I need to do is observe a few properties. First, we should make sure there's actually something in there. And how do I know there's something in here? Well, f of A is less than k, right? So A is in the set S. And in fact, there has to be more than that. You can actually show that there's actually at least some small interval near A where this is, that's contained in S. But there's at least something in S, and often it's enough to say that it's not empty. Okay. Let me also observe that the set S is bounded above. And what is it bounded above by? Remember, S is a subset of my domain, so it's certainly bounded above by B, right? It's a subset of AB, so it's bounded above by B. So it's a non-empty subset. It's bounded above, and what we know about non-empty subsets that are bounded from above, the completeness property of R gives us that the supremum exists. So I'm going to call this supremum C. And now I am guaranteed that the supremum of this set exists. Why am I calling this C? Because I'm going to show that the supremum of this set is exactly the value such that f of C is equal to K. All right. So now what can we say about the C value? I think we're good here. All right, well, the first thing I know is that C certainly has to be less than B, okay? And why does it have to be less than B? Well, what would it mean if the supremum of this set was B, then that would mean that f of B, so I'm just going to quickly sketch it. So if C was equal to B, then f of C minus B minus some small number would have to be less than K. Okay, actually minus any small number. So this has to be true for every epsilon greater than 0, because this value, then this supremum is the least upper bound. Okay, so since it's the least upper bound, if you come down off that upper bound any at all, then you're back in your set, and in this set, f of that value would be less than K. Okay. But think about the function, right? K is between f of B and f of A. And no matter how close I try to put this K here, there's a little range around around B where the function values are still above K, right? Even if you push this K up, there's still a little tiny range there around B. So this can't possibly be true. B can't be the supremum, but it could be anything between, and actually, so you could similarly show that A, is also not in there. So it has to be between A and B. Okay. Let's see. So then what do I want to do? So now I want to show that f of C is equal to K. And I'm going to do this piece by contradiction. So assume f of C is less than K. So I'll sort of do this by looking at two cases. I'll assume that f of C is less than K. Then I'll look at what would happen if f of C was greater than K. I'll show neither of those can happen, so it must be that f of C is equal to K. So suppose f of C is less than K. Then, okay, let me define this quantity epsilon to be K minus f of C. And that's certainly greater than 0, right? If I subtract f of C over here, I'll get that's greater than 0. So I'm just going to define epsilon to be that difference. And since f is continuous, at C, in fact, it's continuous on the entire interval AB, it's certainly continuous at C, there exists a delta greater than 0 such that whenever x minus c is less than delta, f of x minus f of c is less than epsilon. And that's just sort of the definition of continuity. Okay, but remember I've chosen a specific epsilon here, right? So what does that mean? Let's say then f of x in absolute value minus f of c is less than k minus f of c. Okay, so it's just substituting in the value, particular value for epsilon I had chose. Now let's note that, let's see, what is this really telling me then? This tells me, I look at this, if I sort of break this up into cases, right, this tells me that f of x minus f of c is less than k minus f of c. And so if I add f of c to both sides, that tells me that f of x is less than k. Okay. Now, so why is this a problem? Well, then if that happens to be true, then x is in my set S, right? Because x is a value such that f of x is less than k. But notice that x could be any value that's within delta of c, which means there are actually some values that are smaller than c that are in this set of potential x values. So this contradicts the fact that c is the least upper bound, because I should be able to find some other upper bound then that's a little bit closer. Oh wait, sorry. I got that last piece backwards. Sorry, I'm thinking the other direction. So here's the contradiction. There are actually some values then that are slightly larger than c, right? Imagine there's some number like, right, c plus delta over 2. And at c plus delta over 2, the difference here is delta over 2, which is less than delta. But then at that x value, f of x is less than k, which contradicts the fact that c is an upper bound at all, because I've actually found a value that's slightly larger than c that's still in my set S. Okay, so that's a contradiction. You basically work the other way, so then you get f of x is not, f of c is not less than k. You basically run the same thing again, but now you assume f of c is greater than k. If f of c is greater than k, you work through, you reach a similar contradiction, and you get that f of c is not greater than k. If f of c is not less than or greater than k, since this is a total ordering, the only option remaining is that they must be equal. Okay. So that's sort of the intermediate value theorem. Now, remember we said we really need sort of the interval here. Why do we need that? Well, part of the reason really comes back to this sort of completeness property. We need this supremum to exist. And actually, if you take a topology course, you'll actually see that you can do this more generally. But the way we define it is in topology, the way you define continuity is by looking at what are called open sets. We have a very narrow view and analysis of open sets. We're thinking of open sets based on a particular metric, but in topology, you can do this more generally. And so in topology, if the preimage of every open set is open, then you have a continuous function. And then that implies some other things that lead you to a similar type of intermediate value theorem. Okay. All right. So the last thing then I want to talk about, and we actually won't look at the proof of this because I'm going to have you do most of that in the exercises, is I just want to quickly talk about the extreme value theorem. So the extreme value theorem says if f from A to B in R is continuous, then two things. So there exists an x sub m, little lowercase m, in the interval AB, such that f of xm is equal to the minimum value the function achieves on the interval AB. And the second one is essentially the same for maxima, so we call this x sub capital M. There exists an x sub capital M in the interval AB, such that f of x sub capital M is equal to the maximum value that the function achieves on the interval AB. Okay. So the book actually walks you through sort of a proof of a lemma, which is really helpful, and then you get a proof of the extreme value theorem. So I'm going to ask you to sort of justify some of the details there, and make sure you read through that. But again, I just want to point out that sort of one of the keys here really requires, right, again, that this is a function that is defined on a closed interval. So here, actually, the sort of closed bit is the really important bit. It's not so much the interval bit, but it's also not just closed. It's also that this interval is both closed and bounded. So we'll actually look at sort of generalizing this a little bit in the exercise I'm going to ask you to go through. All right, so we're going to stop there for this week, and next week we'll push on. We'll look at sort of one more related thing to continuity, and then we'll push on into differentiation.